Welcome to the wonderful world of physics. This is Physics 104A, Chapter 1, Homework Solutions. We'll start with problem number 11. It says the power output of a typical large power plant is 1,000 megawatts. Express this result in watts, kilowatts, and gigawatts. We're going to start with the given information, 1,000 megawatts, and since it's not already a fraction, we'll make it one by putting it over 1, and we want to convert this to watts. So we'll do the conversion times, and remember mega means 10 to the 6th. So up top we'll have 10 to the 6th watts, down below we have 1 megawatt, and we arrange them in that way so that the megawatts up top and the megawatts down below will divide out, and we're left with units of watts. So we have 1,000 times 10 to the 6th, and that's a billion, or 10 to the 9th watts. Part B, now that we have it in watts, it's a bit easier to convert it to kilowatts. So we have 10 to the 9th watts, which we got in Part A, and we'll multiply that by the conversion, 1 kilowatt over 10 to the 3rd watts. The watts will divide out, and we're left with 10 to the 9th divided by 10 to the 3rd, or 10 to the 6th kilowatts. And finally, Part C wants it in gigawatts. So we take the 10 to the 9th watts that we learned from Part A and multiply by the conversion. 1 gigawatt is the same as 10 to the 9th watts. So we'll do 1 gigawatt over 10 to the 9th watts. And we get 10 to the 9th over 10 to the 9th, which is 1 gigawatt. Number 12 says the diameter of a hydrogen atom is about 0.1 nanometers. And the diameter of a proton is about 1 femtometer. How many times bigger than a proton is a hydrogen atom? I have the given information here. A proton is 1 femtometer, which is 10 to the negative 15 meters. Hydrogen atom is 0.1 nanometers. It's best to get these all in consistent units, and in this case, I think it's best to get it all in meters. So 0.1 nanometers, we're going to convert. Remember that nano means 10 to the negative 9. So I can replace that nano with times 10 to the negative 9. Over here, you can see 0.1 times 10 to the negative 9 meters, which is 10 to the negative 10 meters. Now, when the question asks how many times bigger, it's asking for a ratio. So we're going to put the diameter of a hydrogen atom over the diameter of a proton and find what that ratio is. We know the hydrogen atom is 10 to the negative 10 meters. We know the proton is 10 to the negative 15 meters. And so we get a ratio of 10 to the 5th, which means the hydrogen atom is 100,000 times larger in diameter than the proton. Number 20 says a year is very nearly pi times 10 to the 7 seconds. By what percentage is this figure in error? So we're going to think about the percent error, which is very similar to solving for percent uncertainty in measurements. Here is the formula for percent error. It's the absolute value of the estimate minus the true value divided by the true value. Now we do absolute value in the numerator because we don't really care whether it comes out to be negative or positive. We're just looking for the absolute value difference between the estimate and the true value. This fraction right here will give it to you as a decimal. Then if we want a percent, we're going to multiply by 100%. Now the true value, how many seconds are actually in a year? We have to do that conversion. And here I've got 1 year over 1. And we're going to multiply it by 365 days over 1 year. If you want to be a bit more precise, a year is actually 365.24 days, but this is fine to 3 significant figures, times 24 hours over a day, times 3,600 seconds over an hour, and we get 31,536,000 seconds in a year. So then we calculate the percent error, and you can see I've filled in the values into the formula in the top line. And you can see, you can follow through what I've done here, and I get 0.38%. Now I mentioned that if we want to be more precise, a year is actually 365.24 days. And so I've written down here in green, if you actually do that more precise value, you'll get that a year is 3.156 times 10 to the 7th seconds, and in the end your answer would be 0.44%. Number 21 involves a metric conversion with a volume. How many cubic centimeters are in a cubic meter? So what you should do is start with the given information. We're dealing with 1 cubic meter. Then we do the conversion. We know that a centimeter is 10 to the negative 2 meters. So there's the conversion, 1 centimeter over 10 to the negative 2 meters. But remember, if you only do that conversion once, you're only going to get rid of 1 power of meters. And we need to get rid of 3 powers of meters. So we're going to multiply by this conversion 3 times. And so there you see 1 centimeter over 10 to the negative 2 meters cubed. So we're dividing by 10 to the negative 6. So when we run that, we get 10 to the 6 cubic centimeters is 1 cubic meter. Number 23 says a gallon of paint covers 350 square feet. What is its coverage in square meters per liter? So let's think about the given information. It says a gallon covers 350 square feet. And ultimately, it's asking for coverage in terms of area per volume. So let's set up the given information in that format. 350 square feet per gallon is the coverage. And there you see I've written that in the beginning. Now we need to convert. We need to get square feet in terms of square meters, and we need to turn gallons into liters. So let's deal with turning feet into meters first. We have 0.3048 meters over a foot. And remember to square it so we get rid of both powers of feet. Now we have to deal with the gallons. 1 gallon is 3.78 liters. And so we multiply by that. You notice after various units have divided out, we're left with square meters per liter, and we get 8.6 square meters per liter. Number 28. A 4-part problem says convert the following to use only International System base units. And the first is 55 miles per hour. Well, it's dealing with a speed. It's actually a distance per time. And if we want the SI base units, that means we want meters per second. So we'll say 55 miles per hour. Let's turn hours into seconds by putting 1 hour over 3,600 seconds. The hours in the numerator, hours in denominator divide out. Then we need to turn miles into meters, so 1609 meters over 1 mile. I make sure to cross out the units that divide out, and we see we're left with meters per second. We have 25 meters per second. Part B says 40 kilometers per hour. And again, we want that speed in meters per second. So we start with 40 kilometers per hour. Let's turn kilometers into meters first. 10 to the 3rd meters over 1 kilometer. Hours into seconds, 1 hour over 3,600 seconds, and we get 11.1 meters per second. Part C says 1 week, and it says take that 1 as an exact number. So it's not just one significant figure, it's 1.0000, exactly 1 week. And we want to turn this into the base SI unit, which is seconds. So 1 week, and we'll say there are 7 days in a week, and then 24 hours in a day, so 24 hours over 1 day, and finally 3,600 seconds over 1 hour. The way I've set it up, the weeks divide out, the days divide out, the hours divide out, and we're left with seconds, so 604,800 seconds. Part D says the period of Mars's orbit. Consult Appendix E. So you look up Mars's orbit, you find it's 1.88 years, and we want that in the base time unit, which is seconds. Well, we already found out in a previous problem that a year is, Earth year is 31,536,000 seconds. And so we'll multiply that by that many seconds over a year, and so we get 5.93 times 10 to the 7th seconds. Number 48 says roughly how many Earths would fit inside the sun. And what it's looking at is volume. Another way of asking this is how many times bigger is the volume of the sun than the volume of the Earth? And it's very similar to how the previous prior homework problem was asking about the size of an atom versus the size of a proton. Well, we need the sizes of these things. You can consult the back flap of the book, which gives astronomical data on the Earth, the Sun, and the Moon. Here's the radius of the Earth, 6.37 times 10 to the 6 meters. Radius of the Sun, 696 times 10 to the 6 meters. The volume, we need the volume of a sphere, 4/3 pi r cubed. So now let's set up this ratio. Volume of the Sun over volume of the Earth. 4/3 pi r of the Sun cubed divided by 4/3 pi r of the Earth cubed. We don't actually have to calculate what the volumes are. A simpler way to do this is just set them up in the ratio as I've written it, and you can see that the 4/3 and the pi, they divide out. So the ratio of the volumes, which is what we're looking for, is the same as the ratio of the cubes of the radii. So we have r of the Sun cubed over r of the Earth cubed. To simplify it a bit more, we could say r of the Sun over r of the Earth cubed. So here we have on the bottom line radius of the Sun over radius of the Earth, and cube it. The ratio of those radii is 109.262, and we're going to cube that, so 1.3 times 10 to the 6th. So the volume of the Sun is 1 million, roughly 1,300,000 times the volume of the Earth. And that is the end of the Chapter 1 homework. Have a great day.